Hello there, I'm Brett and welcome back to Math Hacks. Today you get to learn one of the most critical fundamental skills in all of trigonometry. I'm going to show you how to easily sketch the sine, cosine, and tangent graphs by hand. That means that we won't be using any calculators or reference tables. Everything that we do today depends on our solid knowledge of sine, cosine, and tangent. Today's lesson is a really important lesson as we move into more difficult topics in trigonometry, including those tricky graph transformations. We are going to start today's lesson by graphing the sine curve. So I want to graph the function y equals sine of x. Now I've already drawn out my axes. Here I have an x and a y-axis. Notice how I wrote the y-axis offset to the left instead of in the center. Now the reason I did that is because the functions that we're working with today are cyclic or periodic functions. That just means that they repeat over and over again forever in both directions. So my curve is going to go all the way off the page on this side as well as off the page on this side. Now, most commonly, you are asked to graph the two periods at the beginning of the positive side of the x-axis. So that's why I left more room on this side. I will continue the graph a little bit on the left-hand side just to show that this function does continue in the negative direction as well. So the very first thing you want to do after you have your axes is we need to go ahead and section out our x and our y-axis. What's a little bit different about these trigonometric curves is that instead of having normal numeric values on our x-axis, we are going to have radians on our x-axis. So if you think back about the unit circle, remember how when we went around the unit circle, we were working with radians, those pi and pi over 2 and pi over 3 and pi over 6 numbers? That is exactly what we're going to do here. We're going to keep it pretty simple though. I'm just going to section this out with pi over 2 increments because that's all we're really going to need to graph this. Now, as you move into more difficult graphs with transformations, you may need to section it out further into pi over 4s, pi over 6s, or pi over 3s. So I'm going to make sure that I can fit at least 2 periods on the right-hand side of my axes here. So remember that 1 full revolution around our circle is 2 pi, and it just so happens that sine has a period of 2 pi. So I need to make sure that I label all the way out to at least 4 pi on the right-hand side. So I'm going to label these in pi over 2 increments. So this will be pi over 2. And then I'll have 2 pi over 2, which is simply pi. Then 3 pi over 2. And then 4 pi over 2, which reduces to 2 pi. 5 pi over 2. 6 pi over 2, which reduces to 3 pi. 7 pi over 2. 8 pi over 2, which reduces to 4 pi. And 9 pi over 2. On the left-hand side of the axis, I'm going to count backwards by pi over 2. So I'll have negative pi over 2 here, negative 2 pi over 2, or simply negative pi here, and then negative 3 pi over 2 on this last spot. Because the range of sine is only negative 1 to positive 1, that's all we have to worry about labeling on the y-axis. So once you have your axes set up, we are ready to start inserting the important points that define our sine curve. Now, I'm going to show you a trick later on to help keep straight the sine and the cosine curve. But first, I'm just going to walk you through the points. So the sine curve always starts on the origin. So I'm going to place a point right here at 0, 0. Now, what I remember from here is that it always goes up in a positive direction first. So at this next increment of pi over 2, I'm going to place a point at pi over 2 positive 1. Then I'm going to go back down to 0 at pi. And then at 3 pi over 2, I'm going to go to its lowest point, which is negative 1. Now this pattern is going to continue. I'm going to go back up to 0, positive 1, 0, negative 1, 0, positive 1. And that'll continue on and on in the right-hand side. Next, I need to draw the curve a little bit on the left-hand side here. So see how I went up on the right? I'm going to go down on the left. So the next point here at negative pi over 2 is going to be at negative 1. And then I'm going to go back up to negative pi and 0, and then positive 1 at negative 3 pi over 2. All right, now you have all your points plotted, and the last thing we have to do to graph our sine curve is connect the dots. So after you've connected it with a smooth curve, you now see that you have this sine function. Now let's go ahead and take a little closer look at this graph. If you look from 0 to 2 pi, you see that that is one revolution. This picture essentially that starts here, goes up, and then goes down like a little roller coaster. It repeats again here. And if I kept drawing out this graph, it would repeat again here. It would repeat again here on the left-hand side as well. So that's that cyclic nature of these functions that I was talking about. Before we move on to graphing the cosine function, I just want to show you how these points relate back to our unit circle. Now, I'm not going to draw the whole unit circle out, but I do want to draw a few of the key points on the unit circle and show you how they match up with these points here in our graph. Alright, so I just did a tiny little sketch here with just the pi over 2 increments on the unit circle. So here I have a point at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And remember, these correlate to the rotations of 0, pi over 2, pi, 3 pi over 2, and back to the beginning of 2 pi. So if you remember from the unit circle, the y-coordinate always corresponds to sine. So let's see how these values here match up with the points on our graph. So remember, our x-axis represents radians. So at 0 radians, which would be right here, our y value or our sine value should be 0, since I have a point at 0, 0. If I look on my unit circle at 0 radians, my y-coordinate, which is sine, is 0. So 0, 0. That matches up. Now if I go to pi over 2, on my graph I have a positive 1. Let's look here. I go to pi over 2 and look at my y-coordinate for sine and see that it is positive 1 as well. So those match up. Next is pi. So if I go over here to a pi revolution, check my y-coordinate, I should have 0. At 3 pi over 2, my sine value should be negative 1. 3 pi over 2, negative 1. And now when I get back to 2 pi, I see that I have returned to the beginning of my unit circle. And once again, I have a y value of 0. So you can see here, this is how the repeat curve happens. It's because we're basically just using these points that we generated from this circle, this unit circle that we kept going around and around and around. And what that does is it creates a picture that repeats and repeats and repeats infinitely. All right, let's go ahead and move on and graph the cosine function next. It's going to look a whole lot like the sine function, shifted over a tiny bit. All right, so I have my axes here. Again, the first thing I need to do is section it out. And it just so happens that the cosine function, we are going to use these same divisions as we did here on the sine function. So I'm going to count by pi over 2's on the x-axis and positive 1 and negative 1 on the y-axis. All right, so now that I have this all sectioned out, the next thing I want to do is add those important points. So the cosine function, it always starts at a positive 1. So I'm going to place a point right here at 0 radians and 1 unit up on the y-axis. Now, just like in our sine function, it's going to follow the same sort of pattern of falling and rising, falling and rising. So from positive 1 at pi over 2, it will be 0. And then at pi, it'll sink down to negative 1. And then back up to 0, up to positive 1, 0, negative 1, 0, positive 1, 0. And the pattern will continue on the left-hand side as well. Oops. So it will go to 0, to negative 1, and up to 0. And of course, it continues off the page in that same pattern. Next, let's go ahead and connect the dots, and then I'm going to show you how you can keep the sine and the cosine graph straight. All right, so make sure that when you're connecting these dots, that you're doing it with kind of a roller coaster-like curve and not just a straight line, because the cosine function and the sine function, they are these kind of hills and valleys. All right, so now you're probably looking at this and you're going, wow, these two graphs, they look almost identical. How in the world am I going to remember that sine is the one that starts on the origin and cosine is the one that starts at positive 1? Now I have one cool little trick for you, and when I learned this trick, I thought it was really clever, and so I just want to share it with you. Now, the way you can tell the sine and cosine curve apart, if you have forgotten which one starts up and which one starts at 0, is you can take and turn your paper. So I'm going to go ahead and turn this 90 degrees. Now, if you're looking at your paper sideways, and I'm going to use a highlighter for this, and you look at the origin, so here's the origin on both of these graphs. Now, around the origin, you will see an S or a C. So here, right equidistant around the origin, I have this S shape. And then, just around the origin here, I see I have just the C going around equidistant. So see, there's kind of a little C right here. So the one that makes an S going across the origin, that is your sine curve. S for sine. The one that makes a little C going right over the origin, that one is cosine. C for cosine. So that is the way I still to this day have to think to remember which one starts at 0 and which one starts at positive 1. All right, so hopefully that worked for you. If it didn't, that's okay. You can just memorize the points. Now, before we move on to the tangent curve, I do want to go over how the cosine curve relates back to the unit circle really quickly, so you have a good grasp at where these points are coming from, instead of me just saying, yeah, it starts up here, and then it goes down, and then it goes down, and then it goes up, and then it goes up. So let's go ahead and take a look at that. All right, so I'm just gonna put the paper here so that we can squeeze in our cosine graph and this miniature unit circle that I've drawn up here from the last problem. What you need to remember about the unit circle is that the cosine value is revealed in the x coordinates. So if I want to translate 0 radians, looking at my unit circle, 0 radians is right here, and I check the x coordinate of that point on the unit circle to see what cosine is. So the value of cosine at 0 radians should be positive 1. And that matches perfectly with our graph here at 0 radians. I have a point at positive 1. All right, let's try the next one. So the next one at pi over 2, we should have a value of 0. So if I go to pi over 2 revolution on the unit circle, and I look at the x value at pi over 2, I see that it's 0. All right, at pi, I go to pi revolution, and I see that the x value is negative 1. Cosine's negative 1 here. On to 3 pi over 2, I check for the x value. It is 0. Cosine is 0 here. Once I get to 2 pi, I see that I have revolved back to the starting point on my unit circle, and my cosine value there is positive 1. Here on my curve, I am back at positive 1, and I am starting a new period over. Remember, a new picture. So exactly back to the beginning, and then another period is going to start, and then so on and so on infinitely. All right, remember these are cyclic functions. They run in cycles. They cycle over and over again. And most likely your teachers are going to ask for 2 revolutions. And so notice here that if my revolution starts at 0 radians, then here is 1 revolution and here is 2. Your standard window for 2 revolutions or 2 periods of cosine. With sine, we go from 0 also to 2 pi to get the first revolution, and then 4 pi to get the second revolution. So if you're asked to draw 2 periods, that's the picture that you would need to have. And you'd probably want to put a tiny bit on the outside of that with some arrows to indicate that it continues forever in each direction. All right, so the last function that we are going to look at today is the tangent function. And it is a little bit different from the sine and cosine functions. It isn't continuous like these functions, and it has asymptotes. So let's take a look at how that's going to work. So just like with our last 2 graphs, the first thing we need to do is go ahead and figure out how we're going to subdivide out our x and y axis here. Now with tangent, it's a tiny bit different than sine and cosine, and I'm going to give you some tips to help you graph this nice and easily. So the first thing we're going to do is we are going to break this into those pi over 2 units, just like we did on the sine and cosine graph. When you choose how many boxes to use on your graph paper, make it an even number for each pi over 2 increment, because we're going to be dividing it into the pi over 4 increments, and it'll be really nice if you have an even number so you can divide that in half. So I'm going to choose to use 4 units for each pi over 2 marker. And the good thing about tangent is it has a period of pi instead of 2 pi. So in order to get at least 2 revolutions here, I only need to go out to just over 2 pi here and a little bit on the negative side here, instead of the 4 pi that we had to go out to on the sine and cosine graphs. All right, so I've divided my x-axis, and each of these is going to represent pi over 2 units. So the first one is pi over 2 then. Another pi over 2 would get me pi. Another pi over 2 would make 3 pi over 2, 2 pi, 5 pi over 2. Oh, and I have another line here, so I'll just go ahead and put in 3 pi there. And here on the negative side, this would be negative pi over 2. Again, with tangent, we can use the 1 and negative 1 markers on the y-axis. But to make your graph look good, I would make sure to keep the 1 and negative 1 somewhere close to the origin. If you put it too far up, you're kind of just going to get the wrong shape for the tangent graph. So I'm going to just keep it right here and here, just nice and close. So with the tangent graph, at all of the half pi increments lies an asymptote. An asymptote is simply a line that our graph approaches, and the tangent function has quite a few asymptotes. Now, with the tangent function, we know that every single one of its asymptotes represents a place where our graph will never ever cross or touch. And that's because they are places where we would have divide by 0 errors, and I'll explain that to you after we get our sketch drawn. So the first thing that you need to know is that at each of these pi over 2 increments, so all these ones that have a divide by 2 on bottom, are places where we're going to have a vertical asymptote, so a vertical line. And to represent that, I'm just going to put in vertical dashed lines at each of those places. All right, so the next thing that we're going to do to graph the tangent function is at each of these pi intervals, I am going to place a point where y equals 0. So there's going to be a point here, here, here and here. And again, these would continue in both the negative x and the positive x direction forever in that pattern. Now we're going to go ahead and do those subdivisions of pi over 4 that I was talking about. So directly between each one of my increments, I'm going to put a little tick mark to represent pi over 4. And for good measure, let's go ahead and label each of these. So this would be pi over 4. Now I'm going to be counting by 1/4. So that means that if this is 1/4 pi, here would be 2/4 pi, which reduces to pi over 2. And then 3/4 pi, or 3 pi over 4. 4 pi over 4, which equals pi. 5 pi over 4. 6 pi over 4, which reduces to 3 pi over 4. 7 pi over 4. 8 pi over 4, which reduces to 2 pi. 9 pi over 4. 10 pi over 4, which reduces to 5/2 pi. And 11 pi over 4 here. Going in the negative direction, I'd be counting backwards, so this would be negative pi over 4 right here. Now we're going to go ahead and fill in the next important points on our tangent graphs. So from the origin, we are going to be going up to the right for tangent. So at this next tick mark, this pi over 4, I'm going to place a point at pi over 4 and +1. And then left from the origin, I'm going to do the same thing, but it's going to be at -1. So that's going to be right here. I'm going to repeat this pattern for each of these because between each of these asymptotes is a new period. So let's go ahead and add those points in. Okay, now we're ready to sketch the tangent curve in. So what I want to do is I want to fit it to these points, but I also want my tangent curve to get closer and closer to the left asymptote as we go down, and then closer and closer to the right asymptote as we go up. So the 3 points that we included are going to sort of anchor your graph, and then these asymptotes are going to guide it. So I have just see how this curve goes closer and closer to the line as we go down, and it would continue like that forever. So even though it looks like it's going to cross it, it's just going to get infinitely closer and closer and closer to it. The same thing is going to happen on the right, but it's going to be going up. So here I'm going to go up. So see how I kind of have this curvy shape here. That's one period of pi. Here I have another period of pi. It just repeats just like before. Here's another period of pi, and here's the beginning of another period of pi. Since I didn't have all the points drawn out, I don't have the other side of this where the asymptote would be, but this would continue up and do the same sort of thing. Okay. Some teachers do like to include the full revolution, so they'll say it starts at negative pi over 2, 2 pi over 2, and that'll be one picture, and then you can do another picture after that. Some really like to always start at 0, so you kind of just get, and you'll see this in your textbooks a lot, so you'll get this half picture on one side, and then a full revolution, and then they'll end it by cutting it off here in the picture. So that would be your 2 periods, kind of like this one and this one on the ends would connect. Of course, it repeats forever, so you really have it going and going and going in either direction. Okay, so before we wrap up today's lesson, I want to do the same thing that we did with sine and cosine, and I want to show you how these points relate back to that unit circle. So here we have the unit circle, and I just right now have the points on the axes, so our 90-degree revolutions marked. Let's go ahead and start by looking at the point at 0 radians. So here's 0 radians, and I see that my output for my tangent function on my graph is 0. If I check here, remember that tangent is sine divided by cosine. So in order to look at the unit circle and read off tangent, I need to take the sine value and divide it by the cosine value. Remember, the sine value is our y coordinate and our cosine value is the x coordinate. So to find tangent at 0 radians, I go to 0 radians on my unit circle, and then I go ahead and take the y coordinate, which is 0, and divide it by the x coordinate, which is 1. 0 divided by 1 is 0, and that corresponds directly to our tangent graph, where I have 0 radians equaling 0 for tangent. Now let's go ahead. I'm going to do these pi over 4 units here in a second because I didn't draw those in yet. But let's go ahead and look at the next place on our graph, this asymptote at pi over 2. So if I go to pi over 2 in my unit circle, so that's 90-degree angle right here, and I evaluate tangent, so I take the sine or y coordinate and divide it by the cosine or x coordinate, I see that I get 1 divided by 0. Now, of course, we can't divide by 0. So that is why we have an asymptote here. We know that tangent can never exist at pi over 2. Just like when we evaluated on the unit circle, if they asked you what is tangent at pi over 2, you would say it's undefined because there's a divide by 0 error here. So that is what these asymptotes are all about. Let's go ahead and do a couple more. So back to pi here. Here is pi radians on my unit circle. I take the y value, 0, and divide it by the x value, -1. And I get 0 divided by -1, which is 0. Here I have an output of 0. Then when we go to 3 pi over 2, that's down here, and we see once again we get that divide by 0 error. We have a y coordinate of -1 divided by the x coordinate of 0. -1 over 0 is undefined, and that's why we have our asymptote showing up here again in the graph at 3 pi over 2. At 2 pi, we get back to the beginning, which is 0 divided by 1 to evaluate tangent, and we see that that 0, just like this one, is at the point with a y coordinate of 0. Okay, and of course that just keeps repeating as we go around and around the unit circle. Now I'm going to go ahead and fill in the points for the 45-degree or pi over 4 angles so you can see how we get 1 and -1 as the output in our graph. Okay, so I went ahead and drew in the points on the unit circle for those pi over 4 or those 45-degree angles. So I have 1 in each of the quadrants here. Now if I go ahead and evaluate tangent, let's do it for pi over 4, I see that when I take the sine or the y value and divide it by the cosine or the x value, I get square root 2 over 2 divided by square root 2 over 2. So that equals 1, and that's how we get a positive 1 output here. Likewise, if I go to, let's try something different. Let's look up negative pi over 4. So if I go backwards, remember negative radians is a clockwise or a backwards revolution. I go backwards 45 or pi over 4 units, and I get this point. And this point, if I evaluate the tangent there, it is negative square root 2 over 2 divided by positive square root 2 over 2. So that gives me a value of -1 when I divide that, which is exactly what I have here. See how I'm at -1 for my output? All right, so that's just going to be how it is for all of these. I could go to any of these 3 pi over 4 or 5 pi over 4, 7 pi over 4, 9, and then it rotate around and around and around. And I think you get the point by now. So what is really happening here is we are just taking these points that we could generate from the unit circle, from triangles, which is what trigonometry is all about, the study of triangles. We have organized them in this nice pattern. We have defined sine, cosine, and tangent from that. And now, because we can translate these points and the rotations onto its own graphs, where now the rotations are the values or our input values on the x-axis, and our outputs are what sine, cosine, or tangent would be on the y-axis. So hopefully that's all kind of tying together for you now. It is a lot to take in when you first get started, but hang in there, because as you work through these problems and you start to draw all these connections, it all will wrap up really nicely and all fits together, I promise you. Next time, I'll show you how we can easily graph the secant, cosecant, and cotangent graphs by hand as we move towards those problems I talked about in the beginning of doing the graph transformations on our trigonometric functions. If you'd like to stay up to date with this series, make sure to click that subscribe button below or follow me on social media. Till next time, I'm Brett, and thanks for joining me.